All right, so let's solve this problem. Motion of rod AB is shown in the figure. Draw the free body diagram and the kinetic diagram of AB. Then write the detailed equations of motion for AB. We don't need to solve them. We just have to write them in a way that they only contain the unknowns and some constants. All right, cool. So this is going to be some rigid body stuff, and they give us the mass of the bar, but they don't tell us the mass of the motion bars. Okay, but what they do tell us is the motion of bar A. So you kind of have a disjunct. You have some kinematics information and some kinetics information. And generally, that's the way it is for rigid bodies. So for rigid bodies, you have to do some motion, some kinematics, and you generally have to do some forces, some kinetics. So let's look at the motion first, because generally that's the way to work it. So let's look at this kind of segmented. Fortunately, this is a pretty simple body. So let's look at this segment O to A. So I'll call that point A. And they want us to do a free body diagram. Mind you, when it comes down to free body diagrams, we generally need to use mass, force, and acceleration. And so odds are we need to kind of focus on the acceleration values. So let's see if we can figure out the acceleration values of the situation. They gave us the velocity. They told us that the velocity, which is W, equals 4. But they didn't write any acceleration, which means that alpha equals 0. So I'll put alpha equals 0. Okay, because generally they tell you that, or you have to solve for it. But in this case, because it's fixed axis rotation, if it's constant W, then alpha is going to be 0. All right, and they'd have to kind of let you know. So the alpha is going to be 0, which means that the tangential acceleration that it will create has to also be 0, because tangential acceleration is alpha times r, right? But then you can't forget it's rotating, and so you need a normal acceleration. The normal acceleration is going to be W squared times r, which would be 4 squared times 1, which is going to be 16, and that'll be meters per second squared. Okay, so I have my accelerations happening on A. So I can say on this point right here, I now have an acceleration downward, and I have no acceleration to the right. Great. That acceleration, odds are, is going to translate to a force when I start looking at it on the mass that's the rod AB. So for the actual rod that I was analyzing, I was just looking at the motion. There's no mass there. But solving for the motion is going to give me an inclination for how the mass is affected, AB. So that's A. Now we want to do the rod AB. The rod AB. Actually, you know what? I'll do B as well, because if you look at it, let's take a look at our free body diagram again. This zero tangential acceleration, since it's perpendicular, is going to go straight across. And because of the way that the problem is drawn, because of the symmetry, that means that AB tangential is also going to be 0, because tangential acceleration travels along arms and it travels along wires. And so what that means is the same exact thing is going to happen to AB, because AB has the same distance and it's in the same orientation. So because AB has the same distance and orientation, basically this same exact situation is going to happen. So I could draw my arm to B. I know that the tangential is going to be 0 because it travels along just like that. And because of that, what happens is the normal is also going to be W squared times R. So AN equals W squared times R. I just got to figure out what the W is, right? All right, that's not a big deal. Let's look at the velocity. If I take, let me zoom in a little bit. If I take this same guy right here and I look at the velocity, let's do it in blue. This velocity is affected by my 4. Velocity is going to equal W times R, which is 4 times 1. So my velocity is 4 meters per second. The same exact reasoning is going to happen. The same translation of tangential term is going to happen. So that means that if A is moving at 4 meters per second and the bar is perfectly horizontal, that means that B is also going to have the same exact velocity, a horizontal 4 meters per second. Okay, which means that W is going to be the exact same. So it's going to be 16 pointing down. So this has a huge amount of symmetry to it. Okay, huge amount of symmetry to it. So let me erase all those markings I did on the original problem. And I can say, because there's some symmetry here. So taking a look at the bar AB, that's basically my kinematics information. Okay, I just did 2 parts of the 3 that come up with kinematics. So let's do the kinematics for AB. We might need it. So I'll do AB. And then they denoted G, so I'll denote G as well, where G is perfectly halfway through the bar. All right, dope. So we know that when it comes down to it, my rule is for motion, this is going to be 16 and this is going to be 16. If 2 points on the body have the same exact acceleration and or velocity, that means that the object is translating. So because A and B both have the same exact motion, that means that this object is translating. Which means that G has to also have 16, but we have to be able to prove that, okay? Now it's translating, but the thing is, you got to think about the way it's translating. It's translating due to a rotation. This bar is rotating. This bar is also going to be rotating. So what happens is if you kind of draw out the next situation, it will look like this. And then another situation later on where it will look like this. And so it almost looks like a windshield wiper, if you would, where the bar in itself is continuing to have its orientation, but the angle is changing. And so what happens is this is a translation of the bar, but it's orbiting, if you would. I like to say that the bar is orbiting. So this bar is going to be orbiting something, which means that that 16 meters per second that the G is carrying is going to represent a rotation about some radius of curvature. Okay, so it's translating. I'm going to just say it's orbiting something. And when I say orbiting, I mean that it's holding the same orientation, but it's moving at an angle. Okay, and so that's the kind of situation that we're looking for here, and that is super important, the fact that it's orbiting, because we're going to need that when it comes down to our free body diagram. So now I've done a complete understanding of the motion. I understand that A and B are, because of the way the symmetry is holding it, are going to force the rod AB to stay at the horizontal position, but it's still going to be rotating. That horizontal bar is still going to be rotating at the same rate that the bars are, and so that's going to create an orbit. So my free body diagram section, my motion section, is good to go. So I'll put a little check on the motion. Boom. So now we got to do the forces. The forces are our free body diagram. She wants us to do a free body diagram and kinetic diagram of A because A has mass. So okay, I'll put my A and I'll put my B. And then of course we got to denote the center of mass G because that's where all the weight's gonna happen. So when it comes down to it, when you're doing your free body diagram, you want to do your 4 fundamentals. The first one will be your weight, so mg. And that's going to be happening here, and that's going to be 100 times 9.8. Okay. Then you want your reactions to weight. So generally that's normal force or tension. So reactions to weight. If you consider it, something's holding that bad boy up. The reason why the bar isn't falling through the ground is because at points A and B, it's being held up. So point A and point B have to both have normal forces, but they're not. We don't know if they're the same or not. So we're going to call them A and B respectively. It looks like they're probably going to be the same because A and B have the same geometry. But let's say A were longer than B. If A were longer than B, then definitely the normal forces would not be the same because the load will be different. I'm not going to assume that A and B are the same, but I have a feeling that they will be the same. But I'm going to leave it just like this because she wants it in equation form. All right, so I'm going to leave it like that. Number 3 will be my externals. In this problem, we don't look to have any real externals. That's like pushing forces, pulling forces, brakings, thrusts, stuff like that. We don't look to have any of those, so that's fine. And then final be my reactions to my externals. So basically, you're looking at 2 action-reaction pairs, this pair and then this pair. The funny thing is sometimes your reactions and your normal, they actually end up kind of convolving into one set of things. And so based on what we have here, we need to set up more reactions. Why? Because of these accelerations happening on A and B. A and B, when it comes down to the bars that are rotating them, we don't know what those forces are because we don't know the masses of the bar 0A and B02 rather. But on the bar AB, that guy has mass. And so those two, let's put it like this. This guy would end up interacting with the mass of G on the B side, and this guy would end up interacting with the mass of G on the A side. And so that would actually create forces. So what I'm going to do is I'm going to say that's going to be the 16 meters per second, but I got to multiply it by my 100. And this is going to be my 16 times by my 100. And so now I see how the motion is going to directly interact with the mass in itself, okay? So with that being said, it looks like I have my full free body diagram. This free body diagram does not have any x values because we already established that the tangential acceleration is 0. That doesn't mean it's not moving. That just means it's not accelerating. So yeah, we know that it's moving at 4 radians per second, but because that's constant, you can have velocity of 8 and acceleration of 0. It just means that the velocity stays constant, and that's exactly what's happening here. So my free body diagram is done. Now I got to look at my kinetic diagram. Kinetic diagram, you do your AB, and then you put your G. And I like to think of it like this. You have to really understand motion, like the motion purely, to understand how the kinetic diagram has to be drawn. I actually messed this up earlier because I wasn't looking at it in the full sense. You got to really, really be particular. When it comes down to the kinetic diagram, the center of motion, the center of mass G, look at it like a particle. Don't look at it like a rigid body. So you want to understand what that particle is doing. And that's where this whole idea that I said, this bad boy is orbiting something. G is orbiting something. If I were to draw the different situations that G has, at first it's going like that, and then it's here, and then it's here. And you can tell that basically, I'm going to draw some sort of invisible radius of curvature. It's rotating, all right? It's rotating at the same W. It's rotating at the same W and V that the bars are going with. And so that's actually really important, because now that I know it's rotating, I have to treat it like it's rotating. So I can't say that all the forces equal 0, because I know if you're rotating, you can't have a sum of forces equal to 0. You have to have sum of forces equal to a normal and a tangential. And so that's what I'm going to do. I know because the bar is rotating, the center of mass is going to be treated like an orbiting particle, which means it's going to have a tangential and a normal. So it'll be mass times an and mass times a tangential, okay? Now, obviously, there are no x in the in the situation, and so that will be the case. Last but not least, I want to make sure that this object isn't rotating, and so I'll say this is actually going to represent Ig times alpha, the rotation of the actual body. So that's to say if maybe B is rotating a little bit more than A, and that's going to create a general plane motion effect. But generally speaking, you want to have three: a x, a y, and a z, if you would. In this case, our x and our y are going to be rotation variables, tangential and normal, because I know that G is actually orbiting some fictitious radius of curvature because of the two bars holding it on its side. So they're holding it still, and so I have a feeling that my alpha is going to be 0. But this value, I'm sure I'm going to be able to solve for it. So with that being said, I'm going to create a system of equations, and this is our free body diagram and a kinetic. So I'll say, let's just say that this way is positive, this way is positive, that way my normals will be positive, and then I'll say this direction is going to be positive, all right? So what we do from here is we create a free body diagram. We got x, y, and then the moments. And I have to figure out what the moments, which value I'm going about, but that'll be in a second. You know what? I could do m about A, m about B, or m about G. All right. I don't know which one I'll do yet. I'll pick it when I get there. But first, let's look at the x. There are no x forces happening. And so that means that MAT, or AT, equals 0. And basically, that's the proof that shows that since, let's see, since the tangential here and the tangential here is 0, the tangential for the whole bar has to be 0, which means that the bar is not actually accelerating to the left or right based on the tangentials. All right, so that's a simple enough part. So I've just basically shown that this guy goes away. All right, next, let's look at the y's. First, we're going to look at the 1600. So 16 times 100 is 1600, and it's pointing down, so I'll make it negative. And then there are 2 of them, and so I'll say times by 2. All right, then I got minus my gravity, so that'd be 980, yep, 980. And then I got to look at my NA and my NB. Now I assume my NA and my NB are going to be the same, but just to do it the proper way, just put NA plus NB, because I don't know if they're the same or not yet. I'm assuming that they are because of symmetry. All right, and so I'll put a little note there. I'm going to say NA equals NB because of symmetry. NA equals NB, symmetry. Now, this doesn't always happen. Now, I'm only saying that they're the same because they're the same exact bar with the same exact motion. But if there were 2 different size bars, then they would not have the same thing. And so in that case, I can actually put 2N, all right? And that's the left side. So, yeah, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, cool. Now I got to set equal to the right side. On the right side, I have my MAN. And so I can put equals, and then I'm going to say, Because MAN is pointing down, I have to make it negative. Now that's a little bit different from how I'm used to doing it, but it doesn't really matter as long as you catch yourself. So I'll put MAN, where I know AN is going to be equal to, I could put it as W squared times by the radius of curvature, and I'll just write it as a rho. Or I could write it as V squared over the radius of curvature. It doesn't really matter there, all right? But I'm going to leave it like that, okay? So I could replace it if I wanted to replace it. So that's two equations that I have set up, and I now have one equation with two unknowns, right? Odds are, looking at the situation, I know that my AN is 16 because of the my AN of the center of mass is 16. Because remember, this x and this x and this y are both respect to the center of mass. All right, a lot of people mess that up. I already know that my G is going to be 16. And so it looks like I already know that guy. So it looks like I could just solve for n automatically from there. But last but not least, I will do my my moment equations. So you could pick A, you could pick B, or you could pick G that you wanted to rotate about. Generally speaking, if NA and NB were not the same, then you probably want to pick either A or B. Picking G would just create another equation that would have both of them. It doesn't matter which one you build though. So what I'll do is I'll build A and G, whatever. So first I'll do some of our moments about A, and I'll say that this direction is positive. So I'll say about A. All right, so looking at A, I have these two forces touching A. There is no perpendicular distance, right? So it'll be 1600 with no perpendicular distance, in A with no perpendicular distance to A. And so both of those guys would nullify down to 0. And what that's done is that's killed NA from my equation, which is really, really convenient because now I'm going to create an equation that just has NB in it. Okay, so that's equal to 0. Then I have to do the mass, which would be positive because it's going down and around like that. So it's going to create a positive rotation. So positive, and it'd be 980. And then the perpendicular distance here is 2. So it'd be times by 2. Then I have to do positive 1600. And the perpendicular distance will be 4. And then minus NB times the perpendicular distance of 4. Because mind you, we're looking at B, put it in purple, we're looking at where B is going, but with respect to A. And so that distance is 4. Okay, so that's 4 equals, and a lot of people put 0 here, and that's not the way it has to be. Because remember, you're looking at the rotation. So here's the thing. There's two ways to put this. You could put it like this. IG times by alpha, which talks about the rotation about the center of mass. But because it talks about the rotation of center of mass, and I'm focusing on A, I have to use this term and the moment produced by the Y value because it's off the center, it's off the A value. So if I were to write it like that, I have to put plus, and it'd be MAN times 2. That's one way of writing it. Or you could just say IA times alpha, where IA takes into the account the rotation purely about the point A. Or you could say IA is going to be equal to, it's a rod, and I want to say IG for a rod is 1 over 12 mass L squared, and then I have to use the parallel axis theorem, so I'd have to add mass times the distance squared, where the distance would be this little offset, if you would. Okay, so that would be IA, and alpha generally is found by kinematics. Okay, to see how much rotation is being produced. We know that alpha equals 0 in this case, and so it does actually end up balancing out to 0, which is really, really convenient. Okay, so that being said, you can solve for NB purely because now you have one equation. All right, if you didn't know that it was 0, you'd have two equations, and you convert alpha to some sort of acceleration value. Three equations and 3 unknowns, okay? Because we solved that AT, okay? So bam, that's your 3 equations, 3 unknowns, and that's all we have to do. But this looks like it already solves. This looks like it will solve out into something. And so that's really, really convenient. Basically, that looks like it's it. Wow, I didn't have to solve. I did the free body diagram, kinetic diagram. Keeping in account that kinetic diagrams are very important in the way that you analyze them. Your X and your Y piece have to focus on the center of mass as a particle, and the alpha piece has to focus on the rotation of a body about a specific point. Pick your point. It doesn't matter which one you pick. If I did A, it would be like that. If I pick G, let's just do it really quickly. If I pick G, then it would be, let's say this way is positive still. Then I'm going to get negative 1600 times by 2. That's this guy. Then I get plus my Na times by 2, because Na is going backward. My weight piece passes through G, so it doesn't create any moment. Then I'd have a positive 1600, and that comes from the right guy. And then a negative NB times 2. And then last but not least, I'd have to set it equal to Ig alpha, because Ig is now specifically considering rotation about point G. So I put Ig, I put Ig times alpha. But we know that alpha equals 0 in several different ways. And so if that's the case, then it's going to equal 0, which shows that Na, if Ig equals 0, then Na equals Nb because of the symmetry. And that basically is my proof behind this statement right here. That's the proof there. So that's just another thing. But if Ig didn't work out, then a lot of students think that they would have to write those two as separate equations. No. Whenever you write a moment equation, it satisfies a moment equation. You can't write two moment equations and expect them to do anything with each other. These two equations are basically equivalent. You pick one or the other, and you pick them based on the situation. This situation is really easy where it doesn't matter. But there are going to be plenty of problems where you have to pick one specifically because that's the only way that you can solve it, or the ease that you would need to solve it is like vastly different. And so that being said, free body diagram done, kinetic diagram done, and then you write your equations based on the pictures that you set up. So setting up this part right here, I would say, is the hardest. Setting up the free body diagram is not too hard. Just remember that sometimes you need to use kinematics to kind of build it. But then from there, setting up your kinetic diagram, it will wreck you. It's wrecked me plenty of times. And so be very, very careful. Just remember that your center of mass can be translating in traditional XY. It could be orbiting and use normal tangential, or it could be moving in a curve and use radial transverse. It could do all of those, right? And that's a pain in the butt. And so you have to really, really look hard at that. And then look at the rotation of the body in itself, whether it be about points A, G, or B, okay? So that being said, that's that.